Hi everyone, my name is Janhavi and this is my Lab 5 individual video report based on a falling Slinky. So I'll go through some key concepts and ideas for this lab first, then analyze the motion of the mass using tracker. After this, I'll use GlowScript to create a computational model and compare this data with my experimental data. Lastly, I'll go through some of my observations and additional questions. The main aim of this lab is to examine the motion of a falling Slinky dropped from static equilibrium. As the Slinky falls, we will determine the effects of gravity and drag to predict the motion of the Slinky. So here are some of the key concepts that this lab focuses on. When an object is dropped from rest, the only forces acting on it are the forces due to gravity and this drag force. These two forces are acting in opposite directions but do not cancel each other out, resulting in a downward net force, which then results in an acceleration in the downward direction. We'll see this difference between the top and bottom of the Slinky, because the bottom of the Slinky also has the effect of the tension force. So here are some of the key formulas that I use in my lab. I'll be using these in the computational model to predict the object's position and velocity as a function of time. The velocity update formula calculates final velocity, given initial velocity, net force, mass, and change in time. The position update formula calculates final position, given initial position, average velocity, and change in time. Force due to gravity is the object's mass multiplied by the acceleration due to gravity, which is the constant here. Drag force, on the other hand, is equal to the square of the instantaneous velocity of the object multiplied by b, which is the proportionality constant of the drag force. So here's the analysis of the Slinky's motion on tracker. You'll see that I've taken the positive x-axis to point right and the positive y-axis to point upwards. I've also taken the center origin to be the bottom of the Slinky. I've taken the calibration length to be 1.75 meters and the Slinky mass to be 0.205 kgs. I've also noted initial position and initial velocity here, with velocity being 0 as the Slinky is dropped from rest. So here's my GlowScript code for this lab. As you can see, I've taken down initial position and mass of the Slinky. I have acceleration due to gravity and Earth, and the drag force, which I calculated through trial and error by trying to make sure that the final position of my computational data was similar to the final position of my experimental data. So here are my two while loops. The first while loop is for the period of time it takes for the top of the Slinky to reach the bottom, whilst the bottom remains stationary. The second while loop is for when the bottom of the Slinky falls as well. I've used both the velocity and position update formula under both while loops over here. I've also calculated net force using the following formulas. After producing my computational model using GlowScript, here's a comparison between both the observed and model position versus time graphs. The observed and predicted data differ a lot, as you can see over here. This may be due to human error when using tracker for the observed data. Additionally, it may be due to unaccounted forces in the computational model. One way to make the data more accurate is to perhaps track the motion of both the bottom and the top of the Slinky. So let me go through some of my observations and explain the understanding and concepts behind this lab. So yes, the bottom of the Slinky does remain stationary until the top of the Slinky reaches it. Essentially, the bottom of the Slinky stays stationary because of the tension force and weight force, which act in equilibrium, canceling each other out. However, as the drag force increases and this information propagates to the bottom of the Slinky begins to fall. And that's the end of this lab. Thank you so much for watching my video.